Okay, welcome. It's our M-Cubed weekly seminar. And today our speaker is Sergey Frolov. Sergey is the team lead of Reanalysis and data assimilation at the NOAA PSL, Physical Sciences Lab. He's got a PhD in environmental science and engineering from Oregon Health and Science University in Portland. He's an expert in data assimilation and coupled model forecasting. He's well known for formulating and implementing advanced computing algorithms for Earth system modeling. Sergey is presently working on the development of the coupled ensemble forecast for NOAA's unified forecast system. Today's seminar, Investing in the Future of Global Data Assimilation at NOAA, Research, Transition to Operations, and Responding to Emerging Opportunities. Sergey.
Well, thank you for introduction. It was kind of a difficult seminar to put together because I'm, try to balance individual research with a group research, so we'll see how it all unfolds. To give you kind of a sense of where this work is getting conducted, so you recognize Flatiron, that's a NOAA building, and we're located at the south end first floor of the building. So as Rich was saying, so it's part of NOAA. I think with NOAA it's important to show the flow chart. So it's NOAA, research part of NOAA, and we're the Physical Sciences Laboratory, and as part of this laboratory, we have a team focused on model and data assimilation division. And Jeff Whitaker is our team lead, a division lead. And we have two groups, one focused on model development, and Lisa Bankston is a team lead for that. And I'll briefly mention a couple of aspects of her work on physics, but won't be really talking in depth of work of her team. And my team is focused on data assimilation and reanalysis. And I'll give just a snapshot of the research done in my team. I understand that one of my colleagues, Laura Slavinsky, is coming in November, and she'll talk about high cadence data assimilation and probably sparse reanalysis. If you want to learn more about land data assimilation, I suggest you invite Clara Draper to give a talk. And with that, I will talk about the main driver for our work. So this is a National Weather Service product roadmap for global systems, and it goes into bright future, I don't know, 10 years from now. Like at some point, we used to have years here, and now we remove the years because it gets confusing to people. But we're somewhere here right now. We're past the transition of the last GFS system. And what we're trying to do is to take all these different separate system and unify them as a one global system, which will be coupled. And it's targeted for 2024. It will have partial JEDI transition and fully coupled model. The thing that we have worked at PSL was JEDI NKF development. I'll talk about that. I understand there's an interest at MPAS at that, or at MCube at that. LandDA with JEDI was another effort led by Clara Draper out of our team. Physics development was co-led by Lisa Bankston in my sister team. And another effort that we have completed was replay for generating initial conditions for GEFS version 13. So after this 2024 thing is done, we'll be going to the next stretch, like this big stretch of unknown development. But we'll be focusing on transition of atmospheric solver with JEDI to operations, couple LandDA with JEDI, physics development with for UFS, reanalysis for the seasonal forecast system, and rapid cycling. And beyond that, we're interested in strongly coupled DA, using machine learning for data simulation, systematic error correction with machine learning, sparse reanalysis, and variable resolution global modeling. And I'll touch at the end of my talk on some of these more forward-looking ideas. Okay, so probably most of you know, but just to give you a primer, so at NOAA we have a UFS forecast model. So we're sharing the same mediator as NCAR. We have atmosphere. Right now it's FV3 dynamic core, CCPP physics, NOAA model for land. And as many of you know, there's talks about introducing MPAS as a atmospheric dynamic cold core within UFS. For ocean, we use MOM6, SICE6 for ice, WaveWatch 3, and GoCart aerosols. In operational systems, through files, this model talks to GDAS, which is Global Data Assimilation System. And the next transition in 2024 will have JEDI for most of the components except of atmosphere. And we just ran out of time to transition that, and it's a focus of future work. And if you want to put some organizations on different parts of the system, I'm giving some organization pointers here. Okay, so the transition after next, in maybe FY26 and so on, will be to introduce full atmospheric JEDI system, start exchanging some of the information between a model and data simulation system in memory, and start introducing new science. Okay, so I kind of gave you a sense of where NOAA PSL fits in the bigger picture of NOAA Enterprise, and I will spend a chunk of time talking about the things that I've been personally involved, which is JEDI transition towards operations, focus on NKF transition. And then towards the end of the talk, I'll talk about more fun ideas that are more forward-looking. Okay, so I'll do a quick data simulation primer. So data simulation takes all these disparate observations of the Earth system, and we have about 20 million of them in 24 hours. And if I try to visualize them for ozone, they look like this narrow swath of satellite that's really hard to interpret. You combine it with a model and you produce an analysis. An analysis is known to be more accurate than either model or the observations. The specific part of data simulation system we'll be working on is this ensemble Kalman filter, and specifically the GETKF part of it. And why is it important? So different variants of ensemble Kalman filter have been used in operations for a while. And the old variant called LTKF wasn't performing very well with radiance assimilation. So it wasn't doing as well as an operational variational system. And back in 2018, a group of scientists at NRL and NOAA PSL introduced this new GETKF variant, which is the one I'll be talking about later, that does a great job matching the skill of the variational system. So that is a specific aspect of the JEDI transition I'll be talking about. So NKF plays part in not just in a global system, but also in a hurricane system and in a regional system. So it's kind of cross-cutting need in NOAA. We have the GSI is our legacy system, and as many of the things that we do now, we try to upgrade legacy systems to some new forward-looking software architectures, and JEDI is exactly that. So scientifically, JEDI NKF matured tremendously over the last 12 months. We really can start relying on it for doing science. But the throughput of the system is still far from where it needs to be, and that's the focus of our work in the next year. Okay, so if you never saw a transition funnel for NOAA, if you never applied for NOAA funding, that's what it looks like. So you start with the research, low-level research, level 1, 2s, and you do development, demonstration, and deployment. So for JEDI JS NKF transition, there was no research that we needed to do. It was a known system. We just wanted to replicate the capability. So we went straight to development stage. So we developed the abstract layer in OOPS, and I'll kind of give you a figure what that looks like. We also had to do model integration, observation-operated development, and integration testing. And right now, we're in the integration testing period right now. So we're kind of closer to the end of the funnel, the demonstration phase. And at some point, external organizations, even like lab, like NOAA PSL, can't really do enough work, so it becomes all reliant on EMC, where they need to package it for operations. It's not really something that we can do externally. Okay, so what did we have to do to implement this new the NKF in the JEDI system? So JEDI uses separation of concern principle, where we separate abstract applications from abstract containers from abstract interfaces. And then you have model interfaces that implement the specifics of all of those different boxes here. And there's also some shared infrastructure, such as IOTA, for example, for reading of observations, and UFO for making observation equivalents of the model. So this work touched on all parts of the system. We introduced an abstract algorithm, abstract containers, and some reference implementation of FE3 and MOM6. And NCAR team did a great job putting MPass in the system as well. And we had to do some work on the shared components as well. So to introduce NKF, it was really touched almost every part of the system. But the beauty of JEDI was very isolated. So with very limited knowledge of the system, we could come in and introduce what we needed without breaking the whole system. So kind of to talk through a couple of things that we need to do to move that research development into operations. So this work has been led by EMC, JCDA, and NASA. So for each part of the observing system, they had to verify that the JEDI observation operator can match the historic, the well-tested system. So that's this line showing that we can match perfectly 1-to-1. And on the right-hand side here, it shows that in addition to just observation operator, we also need to do quality control and inflate observation errors. And you could see that inflation of observation errors is actually quite situation dependent. So that was a lot of work gone into that. And at this point, most of the observation system has been worked on. And there's a couple of stragglers left. I think aircraft is one of them. So this what's been working for the last year. We're starting to do integration testing. And this is a work done by PSL and EMC. And we picked a couple of high-impact observation systems. So this graph from European Center explains what part of the positive forecast skill comes from which of the observing systems. So MCA is a overall winner across all sensors. ATMS is a replacement for MCA. MCA is a quite old sensor. It went in the air first time in 1998. And CNOP and temperature are conventional observations at ground observing system. So we picked this handful of observation system to try out. And what we found that all the variables match perfectly between historic GSI run and our new runs. The exception is humidity. JEDI is slightly better in humidity if we simulate only radio zones. But as we start adding more observations to the system, the differences go away. So the next big chunk of work we're starting to work on is throughput optimization. So to kind of orient what it means. So this is this square plot shows number of CPU cores on the y-axis and the wall time, how long this job runs on the x-axis. And we use all observations with GSI. We do the forecast first, then the observer, then the solver. And the total time is about 60 minutes. If I reduce the observation network to MCA and zones, the total time gets shrunk up to about 44 minutes. So we'll try to see how close to this target we can get with a JEDI. So the first time we tried it, we didn't get close, so it was over 3 hours. And we realized that one big part of it was interpolation from cube sphere to Gaussian. So we have improved on that, and we shaved off, I think, over an hour. And then the second part that we realized that observation distribution wasn't well balanced, so we improved observation distribution. So now this system is running in 61 minutes, which is still longer than the target of 44 minutes, but at least you can start running experiments with this system. While you'll be struggling to run experiments with a system that was running 3 hours per cycle. Because if you're spending 3 hours per cycle, you're essentially running the same speed as real time. So that was great, and then we started adding more observations. So we added this second most important part of the observing system, this hyperspectral infrared sensors. So what's specific to them, they have hundreds of channels each. Actually, it has thousands, but they seem to be 100. And as soon as we did that, like our throughput got horrible again. So we're like back again to 2 hours per cycle. So we have a pretty good sense of how to improve it. A big part of it is that we're using nonlinear observers for all these hundreds of channels. And if we switch to linear observers, we should be able to shave off almost 90% of compute time in this red square. We can shave off a considerable amount of time. It looks like about 54, almost 60 to 70% of time from the green triangle by working on better I/O. And this little gap here, when we originally compiled this graph, this job was run on a single processor, and we know how to parallelize it. Okay, so I think it's time to kind of set aside this very kind of NOAA specific work where we need to produce an operational candidate and we're working through every single tedious part of what it takes to do it, to something a bit more exciting. So let's talk about a new project. It's a short project, but very short, but very wide project with a lot of people involved called UFS AR. It's motivated by atmospheric rivers that happened in California last winter. So to give you a personal perspective, when I moved to California, that was our pier, and our cement ship at the end of the pier. And then after last winter storm, the pier is gone, the cement ship is broken in two. So it was a really historic event. So I'll have only just one slide about this project, but I think it will be very interesting for people in the MPAS group that work on these multiscale models. So what we're aiming to do is we're aiming to develop a coupled nested UFS model. So what FE3 allows you to do, it allows you to embed a nest. So FE3 is a cube sphere grid. So it's like a cube with 6 faces that gets mapped into a sphere. So and these funny shaped polygons are expression of these faces of the cube when you map it back onto the map. And what you can do in FE3, you can put an inner nest, and ideally you'll have to put it inside of one of the tiles. You could extend it across tile faces, but you cannot extend it across tile vertices. So with UFS AR, we're putting this nest over Pacific Ocean, kind of upstream of California, and including Konos. So it's very similar to Rufus domain, and just shifted west. What's unique about this project, we're also still using coupled models. So there'll be ocean, a quarter-degree ocean coupled to 13-kilometer atmosphere and 3-kilometer inner nest. The scientific challenge is to unify physics that works seamlessly across high convective resolving nest and convective parameterized parent, and unifying all the small, tiny differences that GFS and Rufus team made different. There'll be a refocus and evaluation during the last winter period. GSL is working on unifying the data simulation between Rufus and the global system. And my team is working on the in-core capability of able to run this model without writing files to disk within KF. So another fun project is hybrid physics based in AI forecast models. So give you a, sorry to switch in context so abruptly, but I think it was important to give a sense of what our team is working on for this audience. So what is a hybrid model? So if this is our traditional physics equation, we have a total tendency that's for things like temperature or humidity. And it's part of dynamic tendency, so advection and diffusion. Physics tendency like convection, radiation, boundary layer. And what we're adding to it is this machine learned driven tendency that represents unresolved processes that the traditional models cannot get right. And there's a long history of how to develop this third tendency, and the simplest thing to do is average analysis increments over the season, and it's known to produce great forecasts. Well, good forecasts, improved forecasts. And in the last 3 years, we've been working on using a neural network to learn the systematic error from a history of analysis increments. So to give you a sense how it works, so if this is my analysis increment for some given time for surface temperature, the linear baseline or the average analysis increment, you can see that actually captures an incredibly large part of the total increment. It's something that can be predicted by just taking a seasonal average of analysis increments. We can do it as well by using a column neural network, and we still capture a lot of signal. By eye, for surface temperature, it looks like it doesn't do as well. But if you actually run a long forecast out to 10 days, and you do it many times and collect statistics, what you find is this linear baseline, after a while, will start degrade the long forecast at some portion of the system. But if you put the neural network-based corrections that are state-dependent, it is amazing that we have across the board improvement in the forecast. So the next step for this work is reanalysis specific. So if you look at the history of how
Could
much...
I ask you a question?
Yeah.
Yeah, so what if you to go back to that equation and don't have the first two terms and have it all be on that purple term?
Well, that's coming.
That's coming, all right.
Yeah. Okay, so, but before we get there, let's talk about observational record, going all the way back to 19th century. So part of the scope of our work in our team is producing reanalysis. And if you look at this record, it really is the last 20 years where our record becomes so dense that we can reliably detect systematic biases and systematic model errors. But if I go to 1957, I can barely constrain the initial condition, and there's just not enough observations to detect systematic error. So the idea that we're starting to work on this year is that we want to learn systematic error during 21st century, where we have an incredibly dense observing system, and see if we can improve reanalysis by translating that correction to a sparse era. So to answer your question, Rich, I'm actually just about done. It's the last part of my talk. So how do we respond to this whole revolution in AI and machine learning? The way I start thinking about it, I had to give a talk at the European Center last week. And as part of making this talk, I made this graph. So I put a year at which reanalysis was produced on the x-axis, and log 10 of the CPU that's required was to produce this analysis. And the straight line here is the Moore's law. And I use log 10 because IFS runs twice as fast as FP3, and I can't really get those dots line up if I start accounting for things like that. But it does highlight the trend. And a very basic assumption that if you double the resolution, you have to spend 8 times more computation, and that the cost of 40Y is proportional to the cost of nonlinear trajectory, and the cost of ensemble integration is dominated by the cost of in-K. The in-K, of course, is dominated by the cost of ensemble integration. So if you do this computation, it becomes remarkable that if you look from NCEP R1 produced in 1995 to era 5, which is somewhere here, and to the future reanalysis that we're scoping out right now, we're all in a straight line. So reanalysis and NWP in general were empowered by the Moore's law, but also constrained by the Moore's law. So I was poking around, making my talk, and I was like, well, what's happening with GPUs? And I dug around, and I found this plot. And it shows how the size, the amount of compute people have been using for machine learning from 1952 to present. And it was following the Moore's law up to about 2010. And in 2010, something happened, and the slope changed dramatically, from doubling every 21 months to doubling every 6 months. And then in 2016, it changed again. It slowed down a little bit. Now it's about 10 months. So, and the paper was attributing that what was happening in the first break was when we went to deep learning, and a second break when we went to these large scale models like ChatGPT. So if you dig into literature, so it turns out that it's not just GPUs that enabling these breaks. The GPU is actually not getting that much faster, but it's a combination of hardware, software, and science that enables this break. And a lot of us in this room was thinking that if we just can make our models run on GPUs, that will be the trick. But the experience from the last 10 years in machine learning literature suggests it's not just GPUs. It's a combination of science and software. So the question is, can reanalysis and NWP benefit from this breakthrough in machine learning? And we can't just, we have to embrace it. To embrace this slope, we have to embrace machine learning as part of our pipeline. So to kind of give you a sense, 12 months ago, nobody was really serious about it, and then a couple of papers came out, and the European Center took it seriously, and they started publishing these plots. So on the left here, it's Pangu, it's a Chinese emulator, and on the right here is a IFS high-res model, so the best model in the world, arguably. And what they're predicting is an extreme event. So it's a cold snap over Europe in February 23. Not an average scale, but a very extreme event, way out of the envelope of climatology. So if you're not familiar with this plot, it shows you that the event happened here. So that was a recorded temperature. And the red is a climatological distribution. So you can see that that event was an extreme event. And going back in time along the x-axis kind of shows you how quickly did the forecast was able to pick up this extreme event. And you could see that the switch from climatology didn't happen until, I don't have the date, but until about here, so probably like 5 days out. And the emulator is a cyan dots, and the high-res model is red dots. So what you can actually see here is that the emulator snapped to the right trajectory ahead of either the ensemble forecast from European Center or from the high-res model. That is an incredible result. And the fact that this has been done, this emulator was developed by a team of computer scientists that don't know anything about weather in less than a year of work. It is remarkable. So we really have to do something about it. So my last slide is, so as an NWP enterprise, how do we respond to it? So at NOAA, an obvious question to ask is, what role will these models play in our production suite 3 to 5 years from now? And if you ask this question, it becomes obvious that what we need to do is to do the simulators for coupled models, because our modeling system will be coupled. You also realize that you have to do it for convective resolving models, because most of our compute at NOAA goes towards convective resolving simulations. Ensemble scale is another important part that these models don't do well, but I believe they will. And integration with data simulation method is another obvious thing to do. Another aspect of it, we have large investments in the US and across, and I know specifically in research to operations pipeline, where we build physics-based models, and we always saw that our physics-based model will be used in operations. So what happens when we go to machine learning? So we have to understand how to do transfer learning. Can you pre-train a network on 50 years of era 5, and then have a short simulation with your physics-based high-res model to essentially retune this model to look like, retune the emulator to look like your model that you've spent 5 years developing. What hardware do we need to buy to run these models? New requirements for reanalysis production. If reanalysis becomes a key product that comes out of these high-res models, it will look different than what we do right now. And of course, the whole idea is not to do it faster, but to do it better. So how do we use machine learning to improve forecasts and analysis? And how do we go back and improve our reanalysis so we can train even better emulators? So thank you. I hope you don't mind. It was a short talk.
Okay, questions, comments? Chris, somebody?
So, Sergey, could you say a little bit about when you were doing the machine learning for the analysis corrections, the tendency term that Rich was talking about? How does the machine learn tendency differ from, what does it depend on that wasn't considered in the linear case? And
I have the paper, so Tse-Chun was our postdoc, and he was the first also on this paper. And he had a sensitivity map. So the inputs are temperature, UV, humidity, and surface pressure, I think. And then also a bunch of surface variables and things like solar radiation and time of the year, time of the day, things like that. So it was clearly dependent on the state of the system. Does that answer your question? But he does have a plot that shows sensitivity of the correction to each of those inputs.
okay, I'll look at the paper.
I can repeat the question if you want.
Yeah, just hammering on that question a little bit more. Did you find any benefit, or did you try any non-local predictors? And if you went to something like a CNN that could pick up,
Yeah, so we did not what Tse-Chun did, and there was no benefit.
there's no better.
So that supports the idea that a lot of short-term errors in the 6 hours are based on physics rather than, well, that's an obvious hypothesis to formulate, that they're based on physics errors, not advection or diffusion errors.
Awesome.
Thanks for the nice overview, Sergey. My question was related to the reanalysis correction that you mentioned, that you would learn model error from 20 years and then try to correct the previous period. Question is, what would the verification be to check that
You can
the
still use forecast verification.
before 20 years, is it? And
Yeah, you would run with this third term edit, right?
Yeah.
You do your reanalysis, and then you run forecasts from that, and you
Okay.
see if they verify better.
if the initial conditions are improving
Well,
the
that-
forecast, or
An obvious one will be also to look at the time series of mean increment. And what you see right now is that as observation systems come in and drop out, there's sharp changes in average analysis increment, especially in stratosphere. And that affects the trend.
Right.
So you cannot, using modern reanalysis, you can't represent trends very well.
Right.
So if you can actually represent trends, like if you don't see artifacts anymore with respect to trends, then that's a success.
okay, great, thanks.
So we have, take the Slido question. So we have a Slido question. Can you elaborate on how exactly the linearized CRTM OBS operator will be used for ensembles?
Yes, it will be applied only to perturbations, both modulated and the original perturbations. The O minus B, the innovations will be computed with a nonlinear model still.
And then the second part of the question is, in the ENKFs at PSL, how much compute cost does ensemble integration take up relative to overall costs, DA plus ensemble integration? 60%?
It really depends on the resolution of the model. So this result here is for 1 degree model. So with 1 degree model, it's what, 50-50, 33 minutes for forecast, 60 minutes for NKF. If you go to quarter degree, it probably is 80% forecast, 20% analysis.
Yeah, another question on the reanalysis. So you got the last 20 years. Is this like a 20 CR type reanalysis where you're just using a small subset of the observations, or?
No, the idea would be to run a full run, full input reanalysis for the last, well, the idea would be maybe take last 2 years, assuming 2 years is enough, and learn a systematic error on a full input run for 2 years, and then see how well it will generalize going 10, 20, 100 years back.
Okay. I mean, so there's uncertainties about the changing the number of observations. You just take the last couple of years to keep it constant. The bigger question there is in terms of the machine learning, which has been trained on modern climate. So how confident are you that the trained weights or whatever in the current climate are going to be applicable in the past climate, where the climate has changed probably more than analysis increments? You got to go back, and climate has changed a lot. So
that's a great science question. Well, so Dale, it's a great question. So how would you answer it, given that you don't have any observations in 1900? Almost no observations. Like, how would you go about it?
I don't have an answer. That's probably why I wouldn't do this, because I don't have an answer, because we have no information about what the weights would have been in a climate that's completely different, where we hadn't observed it. So to me, I don't know how you'd solve that. But maybe there is a solution, I just don't know what it is.
I mean, you could go back to 50s, where it was quite different from now, and you can still use verification against radio zones in stratosphere. Yeah. I mean, for big signals like stratosphere or diurnal signal, it will be better. Judith?
Okay. Judith.
Thank you. Thanks. Yeah, thank you very much. You might be able to guess what I'm going to ask. My question is, how can we use either the neural network or analysis increments, etc., to actually improve the model rather than just account for an online bias correction or online model error? How would you go about this? Have you thought about how we actually improve it?
Yeah, so I think we have to regress total analysis correction to individual tendencies. And we could, the easiest, or we could do it kind of offline, and we just output all the tendencies in the model and run analysis and try to do this regression offline. But with this new machine learning tools, you could train an emulator that will do the adjoint, and actually I think that will be a cleaner way to do it.
I had a question about the atmospheric river case that you mentioned. So would you be doing that with weakly coupled data assimilation?
Yes.
Okay.
We only have 18 months, so.
Okay. And would you be assimilating the AR recon observations, the aircraft
Yes.
drop-ons? Is there any plan to do a data withholding test of what's the impact of different observations in those cases?
I think the hypotheses are based on grid refinement.
Okay.
So I think the more interesting questions will be, so now you have this system that has high-res domain and large scale. So you can go do forecast 10 days out rather than just 2 days out, right?
Yeah.
So does your 10-day forecast improve for AR if you go to high-res? Is it important to have the domain going all the way to the date line, or is it just enough to refine the resolution over land? So I think that's the kind of question that will be interesting to ask.
Okay, let's see. Okay, let's go.
Back to the machine learning piece. I'm just wondering if you saw any additive benefit of running, or if you've tried to first run the machine learning to learn the increments, apply those tendencies, and then run your DA on top of it. And do you get more of a benefit to the forecast?
I wanted to do it for the last 5 years, and I haven't had a person in place to do it. So at some point, yes. But
okay.
So my hypothesis is that if you do it only once, then you'll never learn the full bias. So you have to find some way to iterate to actually converge in a full bias.
Sure.
So, but somebody has to try.
There you go.
There are no further comments here. We will retire to the coffee and cookies. And thanks again, Sergey.